Welcome to this course on Introduction to Radar Systems. Since Lincoln Laboratory was formed in 1951, the development of radar systems has been an integral part of our initial mission, developing an air defense system to protect against a polar attack from Russian bombers in the early 50s. But it's also been the development of radar systems has been a major part of many of our programs at the laboratory. Given that, and given that very few courses in radar are available at U.S. universities and have been for decades and decades, the laboratory has been involved in a significant educational program for our staff members to not only keep them abreast of the latest radar technology developments, but to educate new staff members as they come into the laboratory at their different educational levels of the bachelor's, master's, or PhD, to introduce them to radar systems and technology. In 2001, I believe, we realized that a lot of our sponsors could use some of this education too to help them to do their work. And we developed a course that this set of lectures is derivative from. That particular course was an intense 3-day course for our sponsors, military officers and government civilians, those involved in the procurement of radar systems and their technical evaluation and their operation. And not only with the Department of Defense, but also with other government agencies that we do work for, like the FAA and NOAA. And so what we did was we put together a course for their level of knowledge that they'd come into the course with. A typical person coming into the course might be a lieutenant colonel, a very smart person, and he or she would maybe have a master's in business administration. They might have some engineering background, but it might be in chemical or mechanical engineering. They might come from a service academy where they had a diverse background in education. But many of them would not have, they would have had a college degree certainly, but they wouldn't be as involved in the formalism and have the advanced degrees that many of us at Lincoln Laboratory have. So we put this course together to teach them the basic concepts of radar and the technology and the vocabulary of radar, so that when we brief them and explain to them different areas of radar technology, why one technique was better than another for rejecting clutter and seeing targets and that sort of thing, or all sorts of things, they'd understand the vocabulary. They know the difference between the beam width and bandwidth, words you'll get to know. And so we put together this course. And this course is, again, 3 days, very intensive. Now, there's some things that this set of 10 lectures certainly doesn't have. It doesn't have the laboratories. It doesn't have the demonstrations, the tours of facilities at the laboratory. And it certainly doesn't have certain lectures on operational military radar systems that our covenants don't allow me to present to this public audience. But this is the core of the basics of what radar is all about. And there are many people outside of the government who asked us to make this course available to them, particularly military contractors. They have many people in their organizations that they felt this would be a useful course for. Not their engineers who are experts in radar, but people who work in support and administrative areas. And likewise, as I look at the potential audience for this course, there are many in diverse fields in America where a very basic course in how radar works would be very useful. You might be a patent attorney who has come across a patent that involves radar, and you'd like to understand the basics of the nomenclature of what's going on there. It might be you work in the government in the Arms Control and Development Agency, and your background is in the law. You might be in the automotive industry, and radars are being looked at for collision avoidance. small, compact, inexpensive radars. You might want to get an understanding of what this technology can and can't do in a general sense. And that's just the beginning. There are a plethora of people. You might be a civilian air traffic controller, a civilian pilot who wants to know how the radars work that see and keep them safe. So there are lots of different people that this course will be useful for. And this is a first basic cut. We, of course, at the laboratory have a series of courses which delve higher and higher into the technology efforts. And if this course is successful, I hope to put together the next level up, where this would be the introduction, and then there'd be an intermediate, and etc., which would be of use to people with need of a deeper intellect, a deeper knowledge, of the formalism and the mathematics that goes with this. Okay, first I'm going to introduce the whole subject of radar in the first lecture. In other words, in the first hour we're going to do the whole course very quickly and very lightly. First I'd like to acknowledge that, about 2000, early, 6-7 years ago, I taught a course similar to this for our entering Bachelors of Science graduates who would come to the laboratory. Did the whole thing myself. Certainly when one would put together a 3-day intensive course, you don't want to see 10 or 15 hours of Bob O'Donnell in a row, or even interspersed with labs and lectures. So we had a whole series of best lecturers at the laboratory and experts in these different fields work on my set of lectures to modify them and make them optimum for this new audience. And here I acknowledge Eric Evans and Andy Gerber, who provided the managed support and guidance and overall help in putting this, not help, but guidance in putting this whole course together, along with a dozen or so of the key people who took my course, and we all worked together as a team and got the visualizations, the view graphs, to be the best way to help augment the words that the lecturer would say to communicate just how radar works. And these people have just been marvelous, and I'll probably acknowledge through the different lectures an individual person or two as their lecture, when it's clear that they've been just a major contributor in all of this. Something you don't like, blame me. Give them the kudos. Okay. So as I mentioned before, and this is just to recapitulate, it's one of the many courses we have at the radar. This lecture you'll see, set of lectures, is relatively short, 10 lectures. Originally, Dr. Evans and I have given this set of view graphs as a 6-hour tutorial at electrical engineering symposia. And I'm going to be taking more time to go over things. That was compressed, where certain lectures would be a half an hour, certain 45 minutes. There was a time constraint of putting as much as we could in the 3 days. That material is going to take longer because I have the freedom to go over and add more texture to make the course, I hope, a little less like a marathon and more like a walk in the park, easier to digest intellectually. But it will be 10 lectures. We're going to divide the lectures. The introduction lecture will probably be broken into 2 pieces, one a half an hour, maybe the other a half an hour. I'm just going to let the flow go, to say the material, take the time, but not make the lectures, each individual piece of a lecture, each quantum, so to speak, more than a half an hour, so that you can watch half of the introduction in a half an hour, then the other half, and another half an hour. In terms of the scope, as I said, basic concepts and terminology is what you'll have. We're going to have a minimum of mathematical formalism. And as with all good courses, you tell people what the prerequisite is. And really, it's a college degree. Because if you have a college degree, you've probably, in all probability, you've taken a basic course in the physical sciences, which talks about the very basics of electromagnetism. And also, you're going to have taken at least a course in mathematics as part of your general education requirement, which you'll have a solid understanding of algebra. And that's about what we're going to start at the ground floor. And the first lecture, to some people, may seem is quite pedantic, but we'll move on. I'd rather start a little lower and go over certain very elementary concepts and build them up rather than miss a bunch of the audience. I already mentioned who the course was for, and that we have other more advanced courses at the laboratory that we'll be working about. So this is really the outline of the three big things we want to go over. It's really two big things because the course agenda is at the very end, and that's just one view graph going over the outline of the agenda. We're going to spend a chunk of time on why people build radars and what they're for in very simple terms. And I'm going to use an illustrative example from World War II, when radar was first developed, to show you the impact that radar had in a very major way in the strategic outcome of the Battle of Britain. Wow. And we'll go over the basic concepts of the very basics of the flow of a radar and what the basic vocabulary is. And then we're going to take apart each piece of the radar later in a lecture and go over it in detail. Okay. What radar is able to do is, so to speak, lift the fog of war. What do I mean by the fog of war? War is utterly chaotic. Eisenhower said that, and I'm paraphrasing him, that all plans in war are useless, but planning is indispensable. And when he said that first part, that plans are useless, it's because you just don't know what's going to happen. All of you have probably, are watching this, have seen either Saving Private Ryan or the HBO series Band of Brothers. The airborne troops landing, God knows where, far away from where they're supposed to. The utter chaos on Omaha Beach. Supposedly, intelligence said it was going to be defended by conscripts from Eastern Europe, and at the last minute the Germans had brought in a Panzer division. A lot of things that were supposed to work didn't. Going ashore was supposed to be amphibious tanks. The waves were high and they all just about sunk. There was just an awful lot of unexpected happened. And so the ability of not only generals who will run a whole army during that dynamic essence of a war, but the colonels who run their big chunk of it, a brigade or a regiment, the lieutenants that run a company, they want to see what's in front of them, know what's there. And radar is able to wipe away that fog of war. And certainly you can see on the left-hand side in that view graph that smoke is on the banks and the cliffs of Normandy is metaphorical and very vivid of what the fog of war that those brave soldiers were facing when they went ashore at D-Day. And if you go to the Pacific, just the banging together of the general that was in charge of Iwo Jima had 21,000 troops on Iwo Jima, and he said 1 million troops in 1,000 years would not be able to take it. The Allies said, we're going ashore with the usual number, 3.5 times that number, and we're going to take it in 5 days. Well, it took them 25 days, and innumerable deaths and heroism, and it was utterly chaotic. You could mention time and time again the unexpected, and so often you'd like something to tell you what's ahead of you. Okay, so we have military means of sensing, that is to say, what's out there. Electronic systems, and they can be divided up into electrico-optical infrared systems, radar, acoustic, and other. And I'm not going to focus on the electro-optics or the acoustic or other sensors, but just on radar and what their functions are. What is it that they can do? They can give you surveillance to tell you, are there targets out there that we should worry about? And you can track them. follow the targets and see where they are. Direct the interceptors to those targets to knock them down. Use radar to identify the targets. Identify from airborne radars targets on the ground where you can do surveillance, reconnaissance, map where troops are, detect moving targets both in the air and on the ground and in space. Do air traffic control to keep track of your aircraft, whether you're in certainly in this military environment, but air traffic control radars in the civilian environment, very important. You can also put small radars on missiles to help the missiles seek and find targets. Now, what are the attributes that radar has, if you had to list? It can see long distances. If I get up on a mountain and I look out in the clearest of days, I can see an aircraft 10, 15 miles away maybe, a big jet. You can see hundreds of miles with a radar. And also you can see in day and night, and you can see in all weather. You can see through weather. You can locate, here we say in 3 space, that means in both height, angle, and just to know exactly in space, X, Y, and Z, where the target is. And radar is reasonably robust to people trying to countermeasure it. That is, with adding noise, jamming the radar, as it's called, or dropping so-called chaff to give false targets. It's reasonably robust to handle that. Okay, now I want to go into an example, and this is really history to show how radar made such a big difference. In 1936, Great Britain new war was impending, and it built a series of radars at these 21 locations where you see the dots. And this was called the chain home radar system. Okay? And it was all operational in the summer of 1940 when the Battle of Britain started. And Germany started trying to bomb Great Britain into submission. Here we see on the right a picture of 3 of the towers which supported the antennas. This picture was taken about a year ago by a tourist, Robert Cromwell, and these still stand over on by Dover. That's the radar site at Dover. Now, the antennas that were part of this radar, none of them exist. And this is a visualization from technical documents that describe the radars on what this radar system was like. It had redundant antennas, one on the right and one on the left. And the frequencies of the radar the frequency range that the radar operated in was 20 to 30 million cycles per second that it emitted the pulsed radiation. That's a wavelength that corresponds to 10 to 15 meters, 30 to 45 feet. The antennas were quite simple. They were wires, dipole arrays, 8 high. And if you look at this particular configuration of antenna, it reminds one, it was built at this high frequency because that was the frequency that they could build transmitters in those days. They couldn't build transmitters well, or they were just starting to, when the war began, build transmitters of smaller wavelengths, which you'll see later imply smaller antennas than these large structures. The azimuth beam was about 100 degrees, and it had a peak power of the pulse of energy of about 350 kilowatts. It was later raised to 750 kilowatts. And pulses of energy were sent out about 20 times a second. Excuse me, I think it was about 15 times a second. And the pulse width was about 20 microseconds. And that radar had the ability to detect a German bomber at about 125 to 150. And on one of the papers it said 160 miles. Okay? And it used one set of antennas to transmit and another set of antennas over here to receive. If we go to the next view graph, here's what those antennas look like in detail. They are steel towers 360 feet high, and a string of dipoles 8 high. And at these wavelengths, the beam that went out had a big null. The beam went out, and then it had another called a side lobe, but there was a big empty space. And it had another antenna below, which was a set of 4 dipoles which filled in that null. When we deal with propagation, you'll understand more about this effect of the multipath at lower frequencies and what it looks like and why it gives you detection issues. We're also going to study in detail antenna structures. The receive antennas were sets of cross dipoles. So this system was able to see way out 160 miles that the Germans were coming with one of their raids. And remember, they were coming at night. Now, the British had about 1,400 fighters, and they were dispersed at many airfields. And with little warning time, if they didn't have this radar system, which gave them great warning, the British wouldn't be able to concentrate their limited forces to attack the concentrated German forces coming at them. And so there'd be an unevenness to the defending German fighters protecting their bombers, and the British interceptors that wanted to knock them down. The bombers would have got in, dropped their bombs, and got back before the British were able to do much. But with this extra warning time, it allowed the British to get their fighters, their Spitfires, and their Hurricanes off the ground, and that timely warning allowed them to focus their interceptors and achieve numerical parity with the attacking Germans. Why was this all just important? The Germans at this time wanted to invade Great Britain. They knew they couldn't invade Great Britain without air superiority. They didn't have such a great navy relative to the British, and the British had kept theirs in their harbors up in the fjords in Scotland. And if an invasion started to come, they'd bring down their navy and sink the invasion barges. So what the Germans had to do was get air superiority. And it turned out, in the Battle of Britain, they could not achieve air superiority. And the reason is because the chain home system allowed them to concentrate their fighters and wear down the Germans to the point where they said, we just can't do it. It's an interesting anecdote that even though once the Germans attacked the chain home antennas, they never really understood that these were in a crucial radar system that provided that extra warning for the British. And this really allowed the Germans to, it didn't allow them, it denied them air superiority, and consequently the invasion of Great Britain was postponed indefinitely. One can just imagine if the Allies did not have Great Britain as a staging area, the great difficulty that it would have been invading Europe later on in the war. So that's a great example of how radar really made a difference in World War II. Okay. Since then, we have built, and the world has built, all kinds of different radars that do many, many different things. Here's a collage of photographs of a great number of different radars that do surveillance and fire control. And I'll just spotlight one or two of them. This is a photograph of a phased array radar. That's a radar that electronically scans. This particular one is down in Cape Cod, and it gives warning, particularly during the Cold War, if there was an attack from Soviet submarine-launched ballistic missiles. Here's the Patriot radar for the Patriot air defense missile system. This is actually the first phased array, electronically scanned phased array that was ever built in the world. It's down in Florida at Eglin Air Force Base. Still operates and does the majority of the measurement and cataloging of satellites that are rotating around the Earth. Here's a missile defense radar system, and here is on these faces right here and here are the phased array radars with about a 10 centimeter wavelength. The thousands of elements in each one of these two faces. There are similar faces in the aft portion of the ship, and they provide they're the eyes of the carrier, of the battle group, and do air defense for the fleet. Now when we look at airborne and air traffic control radars, here we see a picture of an air traffic control radar, an FAA air traffic control radar. There's one of these in each one of the hundreds, a couple of hundred biggest airports in the United States, and they keep track of all the aircraft within 60 miles of the terminal. Here we see an airborne radar on a KC-135, and the antenna is located in this rotating radome. Here's a photograph of that antenna. This particular radar mechanically rotates in azimuth and electronically scans also. The fleet have airborne radars that give them warning. These planes can get up high and give the fleet warning if there's an attack to the fleet. And fighter planes have in their noses radars that will tell the fighter pilots when they're many, 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 many miles away if there are aircraft heading their way. There's also radars in the Global Hawk unmanned air vehicle. And then there is a class of radar called instrumentation radars that very accurately and precisely measure the characteristics of targets. A number of these are located in Kwajalein in the Marshall Islands, of the ones I've shown you. This particular radar has, I think, 700,000 or 800,000 pounds. It is. It's just huge. It's so big that it has railroad tracks that it rotates on. And here is the facility at Millstone Hill, the Haystack radar and the Haystack auxiliary radar out on Millstone Hill. And there's a 120-foot dish antenna similar to this under the radome, and that emits radiation at just 3 centimeters. And that, building an antenna that precisely is quite a feat, 120 feet across, and you have to keep it to be a parabola to a tenth of a wavelength, or a tenth of 3 centimeters. So an engineering marvel to build that radar way back when it was built. Okay, so now we're down to the basics. What is radar and how does it work? Well, here we see a visualization of an antenna, and behind it, of course, is a transmitter and a receiver in a building, or a shed, or whatever. And that antenna will take the emissions, the microwave emissions, from the transmitter, and a pulse of energy will be transmitted. It will go out and it will propagate through the atmosphere, and then it will impinge on a target. And here we see visualized an aircraft. And that target will then scatter some of the energy back to the radar, where a switch will turn off the transmitter, and earlier it did after the pulse, and listen for echoes. And that echo, the reflected pulse, will be sensed by the radar, and from the delay time of going out and back, one can measure the range. From where the antenna is pointing, you can measure the azimuth and elevation of the target's angles. From the size of the echo, its amplitude, you can measure the target's size. It's so-called radar cross-section. We'll get to what that is in a bit. And also from looking at the frequency of the radiation, the shift in the frequency of the radiation that comes back, you can measure the speed of the target, and also other features with processing such as imaging. And the words radar come from radio detection and ranging. The acronym, these words were used initially when radars were developed, when people were dealing more with radio frequencies, and they didn't really want to say microwave detection, microwave electromagnetic wave detection and ranging. Okay. Now, what part of the, I've been alluding to the fact that these are electromagnetic waves that we're transmitting. And I want to let you know what part of the electromagnetic spectrum that we're dealing with. And here we have a table with some visualizations, that's courtesy of Berkeley National Laboratory, which break up into, it's a logarithmic scale. It breaks up into, each one of these units is a factor of 10 in wavelength. And there's something that tells you how big it is, like 10 to the minus 1, and this is in meters, that's the size of a baseball. And radio waves are very long waves, say that. They're the size of houses and soccer fields. And then when we get down to very, very short waves, we are dealing with like a water molecule size waves, X-rays, gamma rays, and in here are visible waves. And the wavelengths are a millionth of a meter, so-called, 1,000 angstroms. So very, very short. Microwaves are right here in the middle. And radar frequencies operate in the microwave region, and some radars a little bit down in what's known as the very high frequency, ultra high frequency, and high frequency region, but pretty much in this region here, where we're dealing with wavelengths that typically are about an inch to maybe as tall as a human being. That's generally ballpark what the radiation that today's radars. There are some radars that operate in the millimeter wave region, and there are some radars that operate up in 10 meter wavelength region. But most of them, the sizes are down in here. And these correspond to certain frequencies. I'm going to show you how the frequency and the wavelength are related in a minute through the speed of light. But these frequencies correspond to 10 million up to 10 billion cycles per second, or waves per second, periods per second. And you'll hear the words gigahertz and megahertz, and I'm going to tell you what those acronyms mean in a minute if you're not familiar. Okay, so what are the properties of waves? Every wave has a wavelength, and what does that mean? Here we have a simple periodic wave. It's a sine wave, and it's, if you were looking at a wave rippling along on a brook, if you dropped a pebble in and see that wave go out, there's a peak and a trough, and the distance between the two peaks is the wavelength. That's called a period. The distance is a wavelength. The time it takes, if we to watch that peak go to the next peak, is the period of the wave. And 1 over that period is the frequency, the number of peaks per second that go by. And they're related through this formula, that the frequency of the wave is equal to its speed. And since we're talking about electromagnetic waves, which travel at the speed of light, it's the speed of light divided by the wavelength in meters. Now the speed of light is very fast. That's 3 times 10 to the 8th, or 1 and 8 zeros meters per second. That's 300 million meters in a second. And in our normal units, it's you deal with feet and miles. It's 186,000 miles per second. Okay. Now, for the wavelengths that we're talking about, these are frequencies that this corresponds to. So a 3 gigahertz radar, which an air traffic control radar would have the one I showed you, the wavelength is 10 centimeters. Okay, and these show you the correspondence, and they're just related through this formula. Okay, the next concept I want to bring about is phase. You can see that there was that up and down periodicity, and you can measure the phase of one wave relative to another by looking at where one peak is relative to the other. In this case, we have 2 waves that are offset by 90 degrees. So we call that a 90-degree phase offset. And the algebraic expression for this wave is its height or amplitude times the sine of the phase angle. The phase angle over a period goes from 0 to 360 degrees, 0 to 2 pi. Okay? For engineers, they think I'm going too slow. Lawyers are barely remembering this from their trigonometry, probably. Anyway, and we see down here, this would be the algebraic expression. This is going to be very important, that difference in phase, because sometimes if I add the 2 waves together, it's important what the phase is, one relative to the other, whether they add constructively and reinforce or destructively. Okay. Now this talks about that constructive or destructive addition of two waves. In the upper left, we have the constructive addition of two waves. The peak matches the time of the peaks here, and we come out with a wave which is twice the height and the same frequency. If the waves are out of phase by 180 degrees, the peak of one will correspond to the trough of the other. If this is plus A, that's minus A. Add them together, you get 0. You come here at the 0 point, the 0 will add with the 0. So when two waves are out of phase by 180 degrees and you add them, you get 0 output. If they're partially in phase, we have partially constructive, we'll get an answer for the addition in between. Now what we have, if we have just random noise that's coming out, they'll add together and there'll be a partial, because they're not in phase, because the non-coherent noise just doesn't have coherence at all to it. It's the sort of the addition of a whole bunch of random coherent signals, but the randomness is in the phase. And when you add them together, you'll get some addition, and it will be in between, but it isn't as much as you can't get the full coherent addition from non-coherent signals, is what this tells you. Now here we have an example of, I want to go back there, of the concept of polarization. To describe polarization, I have to describe to you what an electromagnetic wave is and how it's generated, and that takes a minute. And right after that, we're going to take a break. An electromagnetic wave is generated in the simplest form by taking an electric charge and accelerating it up and down. If you accelerate a charge, you get an electric field that varies with time. And an accelerating charge is a current that's changing. And that current that's changing generates a magnetic field. And Maxwell in the late 1800s figured out how this all ties together mathematically with a set of equations which really describe electromagnetism. Okay? These are called Maxwell's equations. And with Maxwell's equations, that's the mathematical description. And what that says basically is that when you have an accelerating charge, you generate an electromagnetic wave. And the energy that's transmitted in that electromagnetic wave comes from the charge, the moving charge going up and down. And in the simplest terms, that's how you generate electromagnetic waves. Now, the polarization is the orientation of the electric field vector. Okay? Now I want to go back. And here you see an electromagnetic wave propagating out in this Z direction. And you see that the E field, the electromagnetic field up here, is vertical. It's going up and down. And that's referred to as vertical polarization, when the electric field is up and down. If it was an electromagnetic field that came from accelerating the charge horizontally, the electric field would be moving back and forth horizontally, and that's called horizontal polarization. And you can make, we'll go later when we talk about antennas, we'll talk about other kinds of polarization. Here's an example of the electric field for when it's vertically polarized, the wave is, and here the horizontal polarization example. Now I'm going to take a break, and we'll take a cut to the tape, a break, and then we'll come back and continue the introduction.